Okay, so today we're going to talk about trig derivatives, and we're going to start talking about by talking about sine graph. So let's talk about what the sine graph would look like. I'm going to go over here, and I'm going to go to sine. So remember, there are 4 points on a sine graph that are the important points. And again, remember that its scale is different than normal. It's not a 1-to-1 scale. We are using pi over 2, pi, 3 pi over 2, and 2 pi. Remember, the sine of 0 is 0. The sine of pi over 2 is 1. The sine of pi is 0. The sine of 3 pi over 2 is negative 1, and the sine of 2 pi is 0. They are ones that you do need to know. Here's my graph. And you'll notice that it is the same graph that I have on here. But now I want to talk about the tangent lines. So on your sine graph, I want you, hopefully you've sketched a sine graph on your paper. On your sine graph, draw in the tangent lines at the 5 points that I have listed down here. They are 0, pi over 2, pi, 3 pi over 2, and 2 pi. We're going to graph the tangent lines. Okay? So there's one first tangent line, second tangent line, third tangent line, fourth tangent line, and fifth tangent line. Now 2 of these tangent lines you can figure out what the slopes are quite easily. You should recognize excuse me. This tangent line and this tangent line have a great slope. They are a slope of 0. Slope of 0, slope of 0. Now the question are the slope at 0 and the slope at 2 pi are both the same slopes. And it is an approximation. We're going to talk about approximate what you think it is. If you look at it, it looks like it's approximately 1. We're going to go with 1. But the slope of pi is different. The slope of pi is not positive. The slope of pi is negative. But it does look to be the same slope as 0 and 2 pi. So we're going to go with negative 1. So now we're going to plot these points. Okay? Now whether you plot them above or on a different one, that's up to you. I'll plot them on this one so you can see a couple of things. So at 0, I'm at 1. At pi over 2, I'm at 0. At pi, I'm at negative 1. 3 pi over 2, I'm at 0. And at 2 pi, I'm back at 1. So what happens when we play connected dots? And again, nice curves with sine graphs. Ha! Does that graph look familiar? It should. The purple graph is the graph of cosine x, which means that the derivative of sine x is cosine x. Okay? So that's something that I gotta remember. The derivative of sine x is cosine x. And I have y prime sitting up here. This is y prime. Alright. Let's talk about the same thing with cosine x. Here's the cosine x graph. And again, the important points that we have are the 5 major points, 0, pi over 2, pi, 3 pi over 2, and 2 pi. So again, I'm going to draw in my tangent lines at 0, at pi over 2, at pi, at 3 pi over 2, and at 2 pi. And again, I have some 0 graphs. That's kind of nice. 0 slopes. At 0, pi, and 2 pi, they all have the same slope. They're all slopes of 0. At pi over 2, however, my slope is not 0. My slope is negative. And if you look, well, it looks like negative 1. And at 3 pi over 2, my slope is positive 1. So I'm going to play connect the dots. And I'm going to draw on here. At 0, I'm at 0. At pi over 2, I'm at negative 1. At pi, I'm back at 0. At 3 pi over 2, I'm at positive 1. And at 2 pi, I'm back at 0. So now I'm going to draw this. Well, that graph in purple looks kind of familiar, but it's not exact. If you look at it, it kind of looks like a sine graph, but what's the difference? You notice that the difference is that this graph is reversed or flipped. How do I say flipped in math? It's the negative. The negative of it, which means that the derivative of cosine x is negative sine x. So cosine has a negative in front of its derivative. Alright. And again, this purple graph is your y prime graph. So So here are the derivative rules that you do need to remember. And again, I've got a bunch of them here. Let's talk about these two that I just started. So the derivative of sine is cosine, derivative of cosine is negative sine. Now here's the deal. There's a u there because chain rule does apply. There's a u there because chain rule does apply. So, for example, and this is a random example, if I have y equals the sine of 5x, then y prime is the derivative of sine is cosine of 5x, but that's not a plain old x inside of here. So you have the derivative of that, which is 5. So 5 cosine of 5x. Chain rule, ladies and gentlemen, chain rule. So if you're like, huh? The outside is sine. The inside was 5x. The derivative of the outside is cosine. And the derivative of the inside is 5. And these are the two that I put together. So notice that the very top one is the one that we've done all the time. That's power rule right there. Don't need to copy it down. You should know power rule by now. The next one is the derivative of sine, which is cosine. And derivative of cosine, which is negative sine. Then, we have derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. Now please note, the tangent goes with secant, cotangent goes with negative cosecant. If you look over here at secant, secant goes with secant tangent, and derivative of cosecant is negative cosecant cotangent. Here's how a way to remember these. Number 1, the derivative of all the cos of all. The derivative of all the cosine, cotangent, cosecant, all the cos is always negative. Derivative of all the cos is always negative. Negative sine, negative cosecant, negative cosecant squared. The way to remember it, if I'm talking about the derivative of a cosine, cotangent, and cosecant, my answer is going to be negative. Because the derivatives of cos are always negative, just the way it works out. Here's the other trick to remembering these. The cos go together. Cosecant goes with cotangent. Cosecant goes with cotangent. So cotangent and cosecant squared, cosecant, cosecant, cotangent. You also notice that tangent is secant squared, cotangent is cosecant squared, so they're the opposite ones. One goes with sine, one goes with cosine. Secant goes with secant and tangent, cosecant goes with negative cosecant, cotangent. You have to memorize this chart. This chart is one that you will have to memorize, so hear me now, you have to memorize this chart. It is not an option. So let's talk about the first example that we have. I have 3 of these, sorry. The first one says, find the derivative of y equals sine of x minus 2 cosine of x. Well, the derivative of sine of x, so y prime equals sine of x, the derivative of sine of x, it's just plain cosine of x, minus the derivative of cosine of x is negative 2, is negative sine of x. The 2 is just hanging out there, so I have cosine of x minus 2 minus sine x, correct? And hopefully you've said no, the answer is not correct, and the reason why is that sign that I have that negative sign that I have parentheses around it, because that changes the problem. You don't have those parentheses around it. Because the correct answer would be cosine x plus 2 sine x. There is my derivative. Those parentheses simply make a very big difference. So let's talk about number 2. Number 2 says the sine of 4x plus 5x quantity cubed. Well, this, ladies and gentlemen, because that's not a finite element x, has chain rule. So, y prime equals the outside, the derivative of sine of x, is cosine. The inside, the derivative of 4x, is 4. What goes in those parentheses, what stays there to start with. Plus, the derivative of 5x cubed is 15x squared. So my final answer is 4 cosine of 4x plus 15x squared. Please note that this 4 does not go into the 4x. Okay? This 4 sits outside. You cannot multiply inside that. It doesn't work. You cannot multiply there. The 4 needs to sit on the outside. So let's talk about number 3. Number 3 says y equals tangent of x over 3x plus 1. Y equals tangent of x over 3x plus 1. The denominator has 2 pieces, so you cannot separate it. So I have to do quotient rule. So quotient rule says low d high minus high d low all over the low. Now you'll notice that as I wrote this, I didn't actually take any derivatives. I just wrote out that I'm going to take the derivatives. This is the quotient rule formula. So now I'm going to take the derivatives. 3x plus 1 is hanging out. The derivative of tangent x, if you look above, is secant squared. So it is secant squared x. I may say secant squared, but I am running the x there. That is really important. That variable must be there. So even if I just say tangent, I am saying tangent, I should say tangent x, and then x has to be there. So, and then minus the tangent of x, the derivative of 3x is 3, all over 3x plus 1 quantity squared. Now, question that I love to ask you is, can the 2 that I just underlined be simplified? And the question that I always get, or the answer that I always get is, yes, those can be simplified to the same. I can cancel them out. And the answer is no. The reason I cannot cancel them out is this minus sign right there. So all I'm going to do is clean this up. Y prime equals, it doesn't matter if secant squared x goes first or x 3x plus 1 goes first. It doesn't really matter. Minus 3 tangent x all over 3x plus 1 quantity squared. That, ladies and gentlemen, is your final answer. You cannot simplify it anymore. Whether you leave it with the 3x plus 1 first and then the secant squared x, that's fine. How we had it in green. And some of you can go straight to the red. Some of you don't have to write the blue that I wrote. You can go straight to the green. That's fine. And then simplify. Our numbers do tend to be in front of our trig functions. The numbers do tend to be in front of the trig functions. Alright. So I have 4, 5, and 6. I have numbers 4, 5, and 6. And what I would like for you to do is I'd actually like you to pause the video right now and take about 10 minutes to try 4, 5, and 6. And then you can actually start the second video.